Exercise 8.3, operations involving radicals. Any radical can be written as a rational exponent. So we're just going to have another form that we could take and write square roots as, cube roots. Anything that is a radical can be rewritten with a fractional exponent. The way that we do that, if I have the nth root of a to the m power, whatever the index is becomes the denominator on our fractional exponent. And that will happen every single time. The index from the radical becomes the denominator of the fractional exponent. So here, if I have the square root of 25, remember the index here, even though it's not written, is an index of 2. The exponent on the 25 here, even though it's not written, is 1. Index becomes the denominator of that exponent. So we have 25 to the 1/2 power. Square root of 25 is the same as 25 to the 1/2 power. If you plug that into your calculator as root 25 or 25 to the 1/2 power, either way you are going to get 5. Cube root of 27. Index of 3 becomes the denominator of the exponent. So 27 to the 1/3 power, plug in 27 to the 1/3 power, and you are going to get 3. Operations involving radicals. Radicals act a lot like variables when we use the 4 basic operations. Okay? You cannot add or subtract like terms unless if they have like variables. Same thing with radicals. You cannot add or subtract radicals unless if the radicals match exactly the same. So when I'm looking at these first problem here, 2 root 3 plus root 27, because root 3 and root 27 do not look exactly alike, those are not like terms, I cannot add them together in this form anyway. Root 3, I cannot break down root 3 at all, so I'm going to leave that alone. Root 27, what perfect square is a factor of 27? 9 is, so that's 9 times 3. Square root of 9 is 3. And now look, now we have radicals that do look exactly like root 3 and root 3. And this is where it looks a lot like a variable. If we had 2x plus 3x, 2x plus 3x is just 5x. So 2 root 3 plus 3 more root 3's gives us 5 root 3. Root 50 minus root 8. We first need to break down each of these radicals. Root 50, 25 times 2. Root 8 is 4 times 2. Square root of 25 is 5. Square root of 4 is 2. Now our radicals do match up, so we can subtract them. 5 root 2 minus 2 root 2. If I have 5 root 2's and I subtract 2 of them, I'm left with 3 root 2. So when you add or subtract, the radicals don't change, just like when you add or subtract variables. The variable doesn't change. You simply add the coefficients that are in front of the variable, add the coefficients that are in front of the radicals. Root 7 times root 7. Now, when we multiply radicals, you can multiply things that are underneath. Stuff underneath a radical you can multiply together. Stuff outside a radical you can multiply together, but don't mix things. In other words, don't take things outside the radical and multiply it with stuff inside the radical. Root 7 times root 7. 7 times 7 gives us root 49, and root 49 is just 7. Root 9 over root 16. Anytime you have the square root of a fraction, you can separate it into the individual square root of the numerator over square root of the denominator. Square root of 9, 3. Square root of 16 is 4. Okay, last one here is a FOIL situation. To FOIL these two binomials together, follow your FOIL acronym. First, 2 times 4 is 8. Outer, 2 times negative 2 root 3, and this is where you need to be careful. Do not mix stuff inside a radical with stuff outside. So I can take the 2 and multiply it by 2 to get 4 times root 3. So we have minus 4 root 3. Inner. 4 is outside a radical, 3 is underneath. So 4 times root 3 is just that, plus 4 root 3. Last, taking root 3 times negative 2 root 3. The negative 2 is outside, the root 3's are underneath. So I have negative 2 root 9. From here, negative 4 root 3 plus 4 root 3 cancels. 8 minus 2 root 9. But what's root 9 equal to? That's just 3. So this becomes 8 minus 6, which is not 4, it is 2. All right, last thing here, operations involving rational exponents. This is going to look really confusing when it's all up here together. If you take it step by step, this is going to help you understand how rational exponents become radicals and how radicals become rational exponents. Root x times root x. Change each of these to fractional exponents. Square root of x is the same as x to the 1/2. And now when we multiply like bases, we add the exponents. 1/2 plus 1/2 is 1. That's how we get just x, or x to the first power there. Here, the nth root of x, all raised to the n power, working inside the parentheses first. Nth root, index becomes the denominator of our exponent, so that's why it's 1 over m. Now I have an exponent raised to an exponent. When we have exponent raised to an exponent, we multiply. 1 over m times n gives us n over m, so that's x to the n over m power. Here, 2 steps. Mth root is the same as 1 over m power. Exponent to an exponent in both cases, x to the n over m, times y to the n over m. And then we can go back to radical form. If we work backwards now and go from exponential form to radical form, that denominator has to get moved back to the index on each of the radicals. So we get the mth root of x to the n times the mth root of y to the n. The last property here, very similar to the previous one. Mth root becomes 1 over m as a power. Now we have exponent raised to an exponent. So we multiply x to the n over m, y to the n over m. And now if I want to go back to radical form, denominator becomes the index on the radical, so the mth root of x to the n divided by the mth root of y to the n.